All right, this is Honors Algebra 2 Pre-Calculus. We're doing 5.2 in Pre-Calc, which is verifying trigonometric identities. So in general, when we're asked to verify a statement, right, so I put a sample off to the side here so you can see what I'm talking about. When we're asked to verify a statement, what that's saying is that we don't actually know that these two things are equal, right? That's saying it's our job to show that the left-hand side and the right-hand side are identical. So when we're asked to do that, what that means is that we cannot use properties of equality that we've used all the time with equations because we don't actually know that this equal sign is true. This is a big fat question mark. So you can't add to both sides. You can't subtract from both sides. You can't multiply both sides or divide both sides. You can't do anything to both sides because you don't know that they are equivalent. It's your job to show that. So what that means is that the best option is to change one side at a time and do it in a way that doesn't change the value of the quantity. For instance, you could multiply the left-hand side by 2 over 2 because that's multiplying by 1, which does not change the value of the side. But you can't add 2 to both sides, okay? Or you can't just multiply both sides by 2 because that would change the value of both sides. So generally the easiest way to do this is to pick the more complicated, the uglier side first, right? And see if you can simplify it until it looks like the other side. Sometimes in the harder versions of this, like in the pretty complicated ones, you might have to eventually change both sides of the expression, like the left-hand side expression and the right-hand side expression separately. But again, I still recommend you do one at a time because you don't want to fall into the trap of treating this like it's an equation. So in this situation, if I were going to simplify this, the uglier side is definitely cosine times tangent, right? So what I would do is I'd say, cool, this side is the side I'm not going to change. On the other side, I'm going to recognize that I could rewrite tangent as a sine over a cosine. Well, that means, so again, equivalent expression, right? So that means that the cosines could cancel, and I'm going to get that sine of x equals sine of x, and I'm done. That's it. Left-hand side and right-hand side are identical and are the same. So we're going to walk through some hints on how to approach this. There's no one method. I can't say, hey, this is always the order to do things and it's always going to work. You have to be a little bit creative sometimes, but I'm going to give you some basic guidelines that are helpful. So here are some things you should look for. Can I factor? If I should, or if I can, maybe I should. I should try that. Are there multiple fractions? I should try and get a common denominator and combine them. If something is already factored, can I distribute to make it look like something else? Are there trig functions squared? Then it might be one of those Pythagorean identities. If you see a negative x or a negative theta inside a trig function, that's an even or odd identity. If you see a pi over 2 minus x inside a trig function, that's a cofunction identity. If all of them fail, try changing everything to sine and cosine, which is what I did here, right? Up here I said, hey, look, I could change tangent into sine and cosine, and then it resolved itself. So we're going to walk through a bunch of practice, and that's kind of the plan. So I see this negative inside, right? And my brain says, oh, this is an even odd identity, right, when I put a negative in. So remember, the only even trig functions are secant and cosine. So when I rewrite this, I'm going to leave this guy as my locked box that I'm not going to change. I'm going to rewrite this cosecant of negative x as a negative cosecant of x. And I'm going to rewrite the secant of negative x as a regular secant because secant is an even function, so it doesn't get the negative. And again, I'm trying to show that it equals a negative cotangent x because I don't know that it's equal. That's my job. So I'm kind of at an impasse here. What I'm going to do is, there's no multiple fractions, there's nothing I can factor, but what I can do is take that advice to change everything to sine and cosine. So cosecant is a 1 over sine. So I have a negative 1 over sine divided by, and then the bottom fraction is a 1 over cosine. And again, I'm still trying to show that this is equal to a cotangent x, and I'm not done until both sides say cotangent. So if I work my way up here, I'm going to make this a negative 1 over sine x times the reciprocal of the divisor, which will be a cosine over 1. And I'm trying to show that that equals a negative cotangent of x. So I get that this is a negative cosine x over sine x. And sure enough, and again, I'm trying to show that this equals a negative cotangent x. Sure enough, cosine over sine is cotangent, so this is a negative cotangent x equals a negative cotangent x. Notice I am done when the two sides are exactly the same. All right, moving on. You can go ahead and try this one. Again, just a hint, right? When you see the pi over 2 minus x, right? So pi over 2 minus x, that's a hint that it's that co-function identity, right? So the co-function for cosine is sine, so this is going to be a sine of x. On the bottom, oh, and I'm going to leave this as my easy version I'm not going to mess with, right? So on the bottom, the co-function for sine is cosine, so this is a cosine x. And I'm trying to show it's equal to tangent. Well, sure enough, one of those quotient identities tells me that sine over cosine is the same as tangent. And there we go, right? My job is done when both sides are exactly the same. All right, so when I look at these two sides, right, this one has a cube, and that's not super awesome, but at least it's only one term. So this is the side that I'm kind of going to lock, and I'm going to work with the other side to make it look like this. So I notice that there's a GCF here, that I could take out a GCF of sine x. And if I do that, I'm left with cosine squared x minus 1. And again, I'm trying to show that this is equal to a negative sine cubed of x. Well, this looks like it might be a Pythagorean identity, right? And so I say, oh, I know the Pythagorean identity. It says that sine squared theta plus cosine squared theta is 1, right? So if I subtract the sine over and subtract the 1 over, I get cosine squared theta minus 1 is a negative sine squared theta. And that means I can replace this whole thing with a negative sine squared. So I get that this is the sine of x times a negative sine squared of x. And I'm trying to show that that is equal to negative sine cubed of x, right? And again, I kind of did my work separately here, and I intentionally picked theta not x just to show, hey, this is not the work for the problem. This is separate work off to the side. And sure enough, when I do sine times sine squared, I get a sine cubed, and there's a negative in front. So I get negative sine cubed of x equals negative sine cubed of x, and we're done. All right. So let's try the same thing here. Again, you'll notice one side is much simpler than the other, right? So sine squared seems to be the nice easy side. I'm going to lock that side and make the other side look like sine squared. If I look for a GCF here, right, there is a GCF of tangent squared x, and what seems to be left is a 1 minus sine squared x. And again, I'm trying to show that this is equal to a sine squared, but I don't know it's equal, so there's nothing I can do to both sides, right? Well, I look at this and I think, oh, hey, that's probably a Pythagorean identity. So if I look at the identity that I have here, I know that sine squared theta plus cosine squared theta is a 1. If I want to get a 1 minus sine squared, I could just subtract the sine over, and I'll get that I can replace that with a cosine squared. So I can replace this entire thing in green with a cosine squared of x, right? I used theta over here just to show that I was not, this was not the actual statement I'm verifying. That's just a separate trig identity. So I get tangent squared x times cosine squared x, and I'm supposed to show that that equals sine squared x, right? That's what I'm trying to get to. Well, one more step, if I recognize that there is another ID that says tangent of x is sine over cosine, right? Well, that must mean that tangent squared of x is sine squared over cosine squared, right? So that's another identity, right? So I can replace this guy with sine squared x over cosine squared x, multiplying by a cosine squared x. And I'm trying to show that that equals a sine squared x. Well, the cosines cancel, and sure enough, I get sine squared x equals sine squared x. Both sides are identical, so I'm officially done. All right, for E3, now I have two fractions, right? So I look at this and I say, oh, I see two fractions. My brain says I should probably get a common denominator, right? Probably get a common denominator. So I'm going to lock this side because he's just one little trig function by himself. There's not much I can do there. And I'm going to take this denominator and multiply it by this fraction. So 1 plus cosine x, 1 plus cosine x, right? And I'm going to take this denominator and multiply it by this fraction. So sine x over sine x. And what seems to happen is I get that this is a sine squared x plus, this will be a cosine x plus cosine squared x, right? All over a sine times a 1 plus cosine. I'm trying to show that that equals a cosecant, right? That's my job, is to show it equals a cosecant. So on the top, I noticed that I have a sine squared plus a cosine squared. And they're not in order that way, but they're just being added to a cosine, and my brain says, oh, wait a sec, that's a Pythagorean identity. Sine squared theta plus cosine squared theta could be replaced with a 1. So I get 1 plus cosine x on the top, and on the bottom I get sine x times the quantity 1 plus cosine x. Well, that means that both of these cancel, leaving just the single 1 on the top, right? And again, I'm trying to show that this equals a cosecant, right? So when this whole factor cancels, I just get 1 over sine equals a cosecant. And I know that 1 over sine is actually the same as cosecant because they're reciprocals, so I'm done. All right, let's try a P3. Again, I see two fractions, right? When I see two fractions, my brain says, oh, I bet I need a common denominator, right? So I'm going to lock this side because it's the simpler of the two sides. And I'm going to say, cool, this denominator needs to multiply this fraction, so 1 plus cosine x, 1 plus cosine x, right? And this denominator needs to multiply the other fraction, so 1 minus cosine x, 1 minus cosine x. Sorry, it'll catch up eventually. There we go. All right, so I end up getting that the numerator is 1 minus cosine x, and then a 1 plus cosine x, all over what seems to be a 1 plus cosine x, 1 minus cosine x. I notice that this is a difference of squares, and I'm going to FOIL it. So again, I'm trying to show that this is equal to a 2 cosecant squared x. That's my locked box, right? When I FOIL this, the top, first off, the negative cosine and the positive cosine disappear, and I just get a 2 on the top. And the bottom ends up being a 1 minus cosine squared, right? Because first would be 1 times 1. Outer and inner are both a cosine, and one of them is negative and one of them is positive, so they sum to 0, right? So what ends up happening, cosecant squared. What ends up happening is I get a 1 minus cosine squared. Well, my brain then says, wait a second, I'm pretty sure that this is a Pythagorean identity, right? That's probably a Pythagorean identity. The identity that I would use is that sine squared theta plus cosine squared theta is 1. So I could replace 1 minus cosine squared with a sine. Once I know that, right, once I know that I can replace that with a sine squared, right, I get 2 over sine squared, and I'm trying to figure out if that's the same as a 2 cosecant squared. Well, because 1 over sine is the same as cosecant, this is 2 cosecant squared equals 2 cosecant squared, and we're done because the two sides are exactly the same. All right. Let's do an E4 and a P4, and then I think we're going to move on. All right, so now with this one, it's a little bit harder to see what the nicer side is, I guess, right? So neither of these look nice, but the problem is that I'm kind of stuck with this one for now. When you look at this, it's not fun that it's a fraction, but there's not two fractions, so there's not much I can do to combine it with anything else. So I'm going to lock that for now and see where this takes us. On this side, I do see that there is a GCF. And we can see if that makes life any better, but it may or may not. We'll find out. So we can see if a GCF is helpful. If that's not helpful, then we'll try something else. So one of the reasons I want to point this out is that sometimes you're going to try something, and it may or may not help. So if I try this, I take out a secant, and I'm left with secant minus tangent, and that's not helpful, right? Because all the formulae that I know, all of the formulae that I know so far have involved a something squared and a 1, and that didn't help, right? So since that didn't help, got it. So not helpful. Let's try something else. So I know I could just show you the first step and say, oh, this is automatically what you do, but that's not the way your brain works, right? So you try factoring, that didn't help, okay? Let's try something else. Well, maybe they're fractions, right? So let's recognize that this is actually a 1 over a cosine squared. And this is a sine over cosine times a 1 over cosine. So these are actually fractions with a common denominator, right? And this is still the same thing, right? So I'm pretty sure that they already have a common denominator and that this is 1 minus sine x over a cosine squared. And you might think, okay, how is that better? Well, I recognize that the answer, right? So sine x is the only trig function in the answer on the left-hand side, right? So I think, maybe I could replace this. Maybe I could use a Pythagorean identity to replace cosine squared with 1 minus sine squared. So if I do that, and just to copy this down here, this is what we're bringing down. This is what we're trying to make this equal, right? If I replace that, I get 1 minus sine x on top of a difference of squares. This thing right here is a difference of squares. So if I factor, the bottom is a 1 plus sine of x and a 1 minus sine of x. Sure enough, these guys cancel, and I'm left with a 1 over 1 plus sine x on both sides. Now, that was a tricky one, right? There's a reason I saved it for number 4 on here. So one of the reasons I intentionally didn't look at this right before I started the video is I wanted to look at it with fresh eyes, because sometimes you're going to try something, right? So when you're doing these proofs or these verifying statements, you try logical steps. If it doesn't help, try a different step, right? So try something else, right? And that's part of the issue with this, is that I can't give you a cut and dry, when you do this, this is exactly the set of steps to take. And that's why some people really hate this. So when we go back up for a sec, and then we'll do a P4, but if we go back up to a sec for the hints, right? The first thing I saw was I could factor. So I tried. It didn't help. The next thing I saw is I didn't see any fractions, right? I didn't see anything I could distribute. I didn't see anything that would be very helpful as a trig identity. It definitely wasn't even, or as a Pythagorean identity, it definitely wasn't even or odd. It didn't have any cofunctions. So when all else failed, I turned everything to sine and cosine. And then after I turned it to sine and cosine, I was able to see that it was actually fractions, and then I could combine it. And then I ended up having a factor, right? So sometimes it doesn't go in the order you'd expect, but that's why sometimes these problems can be pretty hard. Most of them are not that difficult. That's intentionally the fourth one out of these. It's the last one in this video that I do by myself, and now I want you to try a P4. Same idea. I'm going to argue that either of these sides could look a little bit complicated, but I'm going to argue that you should lock this side, right? And the reason I'm going to say that is I'm going to suggest that these are fractions, right? If you turn everything into sine and cosine, these are fractions, right? So I'm going to suggest, just to give you a hint to start, that you start here and then see where that takes you. Okay, so pause me if you want, right? And again, we're trying to make this look like secant x cosecant x. All right, I'm going to lock that. So I need a common denominator. I see that they're fractions, so that makes my life a little easier. I'm going to multiply this denominator over here. I'm going to multiply this denominator by the other fraction. And what's going to happen is I'm going to get a numerator that is sine squared x plus cosine squared x over a sine times a cosine. So then I'm going to recognize that this is actually a Pythagorean identity, right? And you'll see how many times we've used that Pythagorean identity. We've used it in almost every single one of these. So sine squared theta plus cosine squared theta is a 1. So I can replace this with a 1 over sine x cosine x. And this might be one of those windows where you recognize that it could be easier, cosecant, where you might recognize it's easier to change both sides. We're going to get to that in the next video. This is definitely one where you could argue that it would be worth changing the right-hand side at this point. But I'm just going to write this as a 1 over sine times a 1 over cosine, because that's the way fractions are multiplied, right? I can write it like that. So that's secant times cosecant. And that would be a cosecant x times a secant x. I can't say I'm done yet, because remember, they have to be literally identical, and right now they are not, because the multiplication is commutative. So, so I'm going to make this secant of x times cosecant of x equals secant of x times cosecant of x. Remember when math had numbers? Oh, my bad. Right, that's a lot of letters. If you ever want to have a little bit of fun, if you have a younger sibling, try having your younger sibling read an expression that's just a bunch of trig functions, because if you can imagine somebody trying to read this, not knowing that it says secant and cosecant, it's sort of a blast. All right, so I believe that that's it for this video.